Welcome, everyone. It's great to see another full house here for this month's Quantum Marketplace webinar. This is an event that's sponsored by the Quantum Economic Development Consortium, or QED-C. I'm Celia Mertzbacher. I'm Executive Director of QED-C. And the Quantum Marketplace program is an important part of our mission to expose QED-C member companies and all of the organizations that are part of the quantum marketplace and the quantum supply chain. And today we're going to be hearing from some of the companies that are a little bit higher up the stack who are working on quantum computing systems. There's a lot of news, of course, about quantum computing, a lot of excitement, and I'm excited to hear our presentations today. So I'll turn it over to the host and moderator, Mark Wippich, to get us going. Over to you, Mark.
Great. Thank you, Celia. Okay, so, just some quick logistics and format. Everyone should be muted except when the speakers are presenting. The speakers should be off of mute. Please send your questions in the chat window if the presenters will be able to access and answer those. And if we get enough time at the end, we'll bring any questions that stand out, time permitting, of course, we can bring into the panel discussion. Also, the recording of the webinar will be posted in the future on YouTube. So in terms of an agenda, I'm going to give a few updates on the quantum marketplace, and then I'm going to give some overview and trends on quantum computing systems. And then we're going to get into the lineup, and then we will have a roundtable discussion, which tends to be very lively and educational, and then give us a quick snapshot on the upcoming webinar schedule. So, just so everyone knows, we have in QED-C, we have one of the pages on the website actually has the quantum marketplace here. All of the member companies are listed with what they actually offer to the marketplace. And we also have a YouTube channel, which is getting very popular now, where we post all of the webinars after we're completed. And if you haven't subscribed, please go there and hit the subscribe button. And also, it's very easy to go there. You can just type Quantum Marketplace in a Google search, and it populates the first page, or you can just type in direct YouTube/Quantum Marketplace. Okay, some quick overview and trends. This is courtesy of Boston Consulting. They've presented in the past in our prior webinars, and just showing and highlighting here that there is potential value creation in over 100+ use cases that are being investigated today with quantum computing. So this is actually courtesy, I lifted this from David Shaw from Fast-Based Insight. And I think he did a great job of comparing, what is quantum computing and how does that compare to classic computing, say in the 90s, and then high performance computing in modern day, and then looking at what happens with the stack from a quantum perspective. And not going to dive into this too much here. We might get into this a little bit later, but there's emerging stack and some challenges here to address, right? And I think there's a lot of questions and confusions about what is quantum computing, and I think one thing to think about is quantum computing doesn't negate classic computing. It's actually bringing together what classic computing does very well and what quantum computing does very well that can potentially bring out better outcomes. And part of that is certain calculations, certain things, are uniquely difficult for classic computers to solve, and it just slows them down. It's not that they can't solve some of these things. It's just very slow. And so quantum computing potentially solves these uniquely difficult problems very fast. And that's where the real value proposition sits, right? And what we're doing today is 4 areas of quantum technology that are attacking quantum computing. This is not an exhaustive list of companies. This is a list of companies, though, that are playing in these 4 areas that are presenting today, right? So there's more superconducting quantum computing companies than IBM and D-Wave, and there's more than Quantinuum and Ion, and there's more than QuEra and ColdQuanta and neutral atom, and there's more in photonics than Xanadu. But I thought this would be a very good thing to look at these 4 leading technologies that are essentially you can access all of these on the cloud today, or you will be later this year, according to these companies. Also, there are a few other technologies. We're not highlighting them today. They're a little bit further out in terms of commercialization, but just keep in mind as you're investigating these things in the future. And I like to remind everybody here that, so quantum advantage disruption is coming. Many of us believe that. And it's really good to get started, when it's here. It may be too late if you wait, if you're just curious about this, your organization should probably start taking a look at it now, because it might be too painful to catch up later. So, perhaps taking the dual approach of utilizing a strategic downside risk mitigation while having a seat at the table on a potential upside opportunities is the best option. Okay, so with that, we're going to get into the lineup here. We're going to have Jerry Chow from IBM go first, and then we're going to have Murray Thom from D-Wave, and then we're going to have Brian from Quantinuum, and we're going to have Pedro from QuEra, and we're going to have Paul from ColdQuanta, and we're going to have Raph from Xanadu. And we have a very extensive list here. It should be very exciting.
Thank you. So yeah, my name is Jerry Chow from IBM Quantum, and what I wanted to talk to you about today really quickly is just to tell you where we are, right? And I think it's actually a very exciting time for me just today, because actually yesterday was 6 years anniversary for us to put the first quantum system on the cloud. It was at the time called the IBM Quantum Experience, and it was a 5-qubit quantum processor that we placed over the cloud, connected to a simple composer for developing and running quantum circuits, really opening this entirely new avenue for doing experimentation and doing in quantum programming on an actual system outside of a traditional physics laboratory. And now since then, right, there's just been tremendous uptake of quantum. And from our perspective in IBM, we've done a tremendous amount to accelerate this pace of adoption. In those 6 years, we've now today have over 20 plus operational systems accessible over the cloud today, touching over 400,000 users with a business network in our IBM Quantum network of over 180 institutions and members. And altogether, we're seeing executions of 3.5 billion circuits daily. I think that's really the core thing, right? Which is that we are seeing this exponential growth in terms of this adoption, in terms of the number of circuits that are being run. We're looking at cumulatively over 1.6 trillion circuits that have been run on our platform and hardware to this date. And so today, right where we're at is we have those 20 plus systems online, including a 127 qubit quantum processor called IBM Washington, a number of 65 qubit devices, and a few 27 qubit devices. And there are various metrics by which we measure the performance of these, and they some of them are freely accessible, and some of them are accessible through our quantum network. Now, a big part of where we see the path, though, is there's a roadmap to continue to drive the performance and enable basically the ecosystem to further develop and find applications of with quantum advantage and quantum impact over the coming years. And so last year, we actually in 2021, we actually released this very detailed development roadmap with a foundation of quantum systems and hardware that show a scaling roadmap and a scaling path by which we're continuing to push on the number of qubits, but also other parts of the stack as well, in order to show how we want this ecosystem develop, where there's going to be the need for different types of developers. A big part of what our whole strategy involves is having that underpinning of our foundational hardware with an open source platform with Qiskit sitting on top of it. And Qiskit, for that matter, touches a number of different types of developers, from those that might need closer to the qubit control with kernel developers, to those that want to develop algorithms, and to those that might just want to be developing new applications in terms of in the areas of interest, such as in optimization, finance, machine learning, or chemistry. And so a big part of this roadmap is to continue to hit the various targets, right? Year after year, we wanted to continue to push the envelope along this roadmap. At the end of last year, we demonstrated our scaling path towards 127 qubits. This is our Eagle processor. It's the most advanced quantum processor out there in terms of in terms of its performance, in terms of the multi-level wiring and the integration of really CMOS techniques to make this system and make this processor work. And then along with that, we've had new generations of control electronics for scalability and affordability in order to really meet those end goals of deploying these systems reliably. Complementary to that is a drive to push performance of the systems in terms of quality. This is through with our superconducting qubits driving coherence. I've seen a 3x increase in those in some of our 27 qubit devices. Reducing gate errors, increasing gate fidelity. Recently, we showed 3 nines of gate fidelity, and then pushing on a performance metric we call quantum volume, and recently hitting quantum volume at 256. And then a third element of performance besides scaling and besides quality is speed. And this is really critical, especially for running problems of interest where we really need to be able to run a lot of circuits. For a simple chemistry problem where you want to get a very accurate estimation, for example, for lithium hydride, we're talking about potentially billions of circuits. And so the total amount of runtime that you have for your quantum circuits on your classical and your quantum hardware is really critical. And the amount of time that you have there is really governed by the type of quantum hardware. So for superconducting qubits, that's why we're talking about circuit repetition times in the microsecond range, which gives you a solution for certain types of these problems that are really tenable, right, in terms of a few hours versus perhaps a better part of a year, depending on a different type of architecture. Now, what we're continuing to do is to drive partnerships throughout the world, right? We have these systems that are not just in our quantum data center in New York, but we have one now that is out in Germany and one in Tokyo, and we're continuing to look to enable these ecosystems throughout the world and drive regional growth, both in the hardware space as well as in the software development application space. And then just touch on also that we have a number of those 180 members in the business ecosystem that are actively researching using the systems to explore novel areas of application that will make use of quantum advantage as it comes around and as our performance of our systems improve. And then, yeah, just to frame it back together, this is why we have this roadmap, right? Calling our targets for the coming years and how we're going to continue to push forward. This year, we're planning for our Osprey processor, 400 plus qubits, and enabling a number of other elements of the entire stack. With that, thank you.
Hi, everyone. My name is Murray Tom. I'm the Vice President of Product Management at D-Wave Systems. I'm excited to be here today to talk to you about D-Wave Systems and what we provide. I think the first place I want to start is just begin at the beginning here. What is a quantum computer? If we think about the computers in our everyday life, like our laptops and our phones, if you reach in and you pull out the computing chip in there, that's what's doing the information processing for you in a computer. And if you go into that chip, that CPU or GPU, and change its fundamental building blocks so that they can now behave quantum mechanically, but more importantly, behave quantum mechanically in a way where that's going to accelerate your information processing, you've just made that a quantum computer. And in that way, that's different than any other computer that's on the planet. Okay, so fair enough. If we give them quantum mechanical properties, how are we actually going to use that to accelerate information processing? So there's two principal ways. One is that you can use those quantum states to store more information in your computer memory and to process over that. And that's fantastic. That's called the gate model of quantum computing. It enables some very powerful algorithms. It also has some sensitivities. If the quantum state collapses, it can actually destroy that information, which is part of the reason why we have error correction schemes for recovering it. There's another mode for using the quantum mechanics to help accelerate information processing, which is to use the quantum mechanics to move through solutions quickly. And this is usually referred to as the quantum annealing model. The great thing about this is that if the quantum state collapses, the movement between solutions will pause, but after the end of the pause, the quantum state will reemerge and you'll continue moving through solutions. So both of these are ways that we can leverage quantum mechanics to accelerate information processing. And D-Wave is the only company building both types of technology because we want to be able to provide the technology necessary for your full quantum use cases. But having said that, this isn't about technology. The quantum computing industry is about helping businesses, governments, academics, and users to achieve their objectives more efficiently. So let's focus our conversation here about practical quantum computing and the ways that we can make use of it. Here's a compulsory legal slide. So at D-Wave Systems, we have the world's most powerful and connected quantum computers, the D-Wave Advantage systems with over 5,000 qubits and 15-way connectivity. And what's really different about these systems is that they're currently available in the cloud right now. And you can begin programming on them immediately and start working on getting demonstrations of application value for the applications that you're working on. We have a cloud platform with an integrated developer environment. We've got Python, open source Ocean tools that you can use for problem formulation as you're programming those systems, as well as a support site and user forums for you to collaborate with others. Now, through that LEAP system, you can make use of hybrid solvers. And this is not about hybridizing and looking at the way that quantum computers use. This is about achieving more results at application scale quickly. In these cases, when you're programming these systems, they actually deploy classical computers in the cloud that start working across this full application scale problem, breaking out pieces, submitting them to the quantum computer, and then reincorporating them in the solution. So it's a very powerful mechanism to allow you to get to up to 1 million variables for some binary quadratic model formulations, or if you're working with problems with constraints, up to 100,000 constraints, really enabling you to get to like enterprise scale application problems and demonstrations of real value. We get asked, are people using this? These systems right now? Absolutely, they are. Here's a selection of a series of customers in different sectors, the types of applications that they're looking at, and the phases of that development that they're going through. So typically beginning with application evaluation, looking for the places in their business where quantum computing technology could disrupt and provide big advantages for them, developing to proof of concepts at application scale that then move to a pilot deployments, and then to actual full production scale deployments, with some examples, for instance, being the development of new OLED materials and also protein design for medical therapeutics. Now, when I'm out speaking at developer conferences of people who are looking to program quantum computers and application, they sort of tell me if I knew more about what a quantum computer could do, I'd be more interested in learning about the technology. Here's a set of examples with Minton that have done quantum design proteins that have been synthesized and taken to live virus testing against COVID-19. Save On Foods, which is using this for grocery optimization for their complicated business that includes ordering, at-home delivery, and brick-and-mortar store operations. They've been able to take some important grocery optimization problems from 25 hours down to 2 minutes. Denso has been looking at applications of optimizing their manufacturing floors, particularly the movement of autonomous vehicles, autonomously guided vehicles through the floor, and even optimizing for safety. They were able to demonstrate a 15% reduction in the time spent waiting for the movement of those vehicles. And OTI working on the OLED quantum chemistry examples. Now, I've got more here than we can possibly read or go through. This is just meant to be something as a reference to let you know what's possible here, but there's a number of companies who are working in financial services and data or portfolio optimization. We've also got examples here in manufacturing, logistics, and mobility. GrooveNuts has actually done some really interesting work on optimizing waste collection vehicles in order to reduce CO2 emissions, so really important applications for sustainability. And Savantex has done some work optimizing operations at the Port of LA in order to make their throughput more efficient, which is a really important part as we're looking at applications to do with supply chain logistics changes and adapting to those and really allowing organizations to be more efficient and effective at what they're doing, as well as a variety of applications in life sciences, which is, of course, something that's really important to us with a variety of companies working through this. So I'll just pass over this briefly. This are the phases that we typically see businesses working through as they're looking to apply quantum computing to their applications. And I'd encourage you to check it out and follow up with us and find out more.
All right, thank you for having me. My name is Brian Ninehouse. I'm the director of our commercial operations group at Quantinuum, and today I want to talk about our trapped ion-based quantum computing hardware. So Quantinuum is sort of a new company. We were just formed this last November with the merger of Cambridge Quantum and Honeywell Quantum Solutions. Together, that's Quantinuum, and we've got offices here in Colorado, where I'm based, along with Minnesota, in the UK, Germany, and Japan as well. Working on both quantum hardware using trapped ions, as well as quantum software and quantum algorithm development. So the center of our quantum computer is based on trapped ions. Here's a picture of our trap, where we grab onto these ions and manipulate them using this surface electrode ion trap that we fabricate up in Minnesota. And we follow an architecture that was proposed quite a while ago by the NIST ion storage group, just up the road from me here at Boulder. And they proposed at that point that you could build a large-scale quantum computer using trapped atomic ions because they're easy to grab onto with electric fields and move around. So by fabricating some complicated electrode structure, you could physically move your qubits around, move them in and out of dedicated zones for high fidelity single and 2 qubit gate operations. And then you could scale this up by adding more and more zones. And this was, they coined the phrase back then that this was this QCCD architecture, this quantum charge coupled device, making the analogy between how these ions are moving around within this complicated quantum computing device and how electrons are shuttled around at the back of your CCD sensor, say in the back of your digital camera. So we follow this architecture. Here's a schematic of the trap that's in our current commercial systems. All of our qubits sit in a line here at the center of the trap. And then all the various electrodes, which are shown here in different colors, shuffle these qubits around, moving them in and out of the interaction zones where they interact with the laser beams to do quantum gates, as well as reconfigure the ion chain, ordering and pairing up the qubits however we want to execute an arbitrary quantum circuit. And I would say that this commercial computer we have now integrates all the necessary ingredients that were proposed back in this paper by the NIST group, and has all the ingredients for a scalable quantum computer, even though it is sort of a small system at this point. So I'll brag a little bit about the QCCD architecture and some of the advantages it has. The first is that it natively has all-to-all connectivity, that because our qubits are completely reconfigurable, we can move any two next to each other and perform a quantum gate in a single step. And this is a great advantage over, say, architecture with fixed geometry and local interactions, where you might have to do a series of logical swaps, each with error, to get information from one side of the device to the other. Here, you don't have to worry about the geometry of the trap because it's reconfigurable. We can move the qubits at will. Say it also has very high fidelity gates because our qubits are always isolated and moved into specific zones for these quantum operations. We can have very high single and 2 qubit gate fidelities as well as state preparation and measurement. But I think an important thing to point out here is that this high fidelity also stays as we scale because this basic building block remains the same. We don't have to worry about extra crosstalk because we're just scaling up the classical control around the qubits. The basic interactions between the lasers and the qubits stays the same. So we expect these fidelities to stay high even as we scale. And then the last feature I'll point out today is that it also gives us a very straightforward ability to measure a qubit in the middle of a quantum circuit and then reuse that if we want. So we can, because the qubits are mobile, we can move just the qubits we want into the interaction region and measure them while all the other qubits are out of the way and their quantum state can remain intact even as you measure some subset of qubits in the machine. So this can help us efficiently use ancilla qubits over and over again by using them and then resetting them and using them again. It also allows us to do conditional logic where you can measure something in the middle of a circuit and make a decision while the circuit's still running. So a quantum if statement, if you will. And this is an essential ingredient that everyone needs to develop to get to quantum error correction. You need to be able to measure syndromes and feedback them in real time, but it's quite straightforward to do because of the mobile nature of our qubits. So if you have quantum circuits that you're ready to run today, there's a couple of very straightforward ways to gain access to our machine. Oak Ridge National Laboratory has a quantum computing user program that you can apply for, just a short proposal on the project you're trying to do and gain access to the machine, as does Azure Quantum. They have their credits program through Microsoft there that you can gain access to the machine in very short order. If you're not ready to write your own quantum circuits or want to talk more about applications or help with algorithm development, this merger gives us lots of teams across the company with expertise in all sorts of subject matter. You should contact us directly at qcsupport@quantinuum.com. Thanks.
All right, nice to meet everybody. My name is Pedro. I'm a business developer, and I'm happy to introduce you today to QuEra computing. So at QuEra, we build and operate quantum computers with the mission of providing the highest attainable degree of quantum advantage at every era of quantum computing. Now, to do that, we have picked a technological direction that is different from the ones that you have heard so far. This disruptive technology based on neutral atoms. And we've picked this direction because of the outstanding capacities and for scaling of this technology, and because it has been continuously delivering also very strong results in applications in the past 4 years or so. So this technology again uses atoms and uses lasers, but it should not be confused with ions, and it should not be confused with photonics. These are neutral atoms. Because they are neutral, it means that we can pack them very densely together without them complaining. They don't repel. Because of that, we can create reconfigurable architectures. Our geometries are not fixed. As I just mentioned, we have a very scalable platform. Besides that, these machines, they operate in room temperature, so there's no cryogenics in our labs. And the interaction of our qubits is also not local. And this technology also allows for separate storage and processing zones. So it really combines the best scenario of every possible direction that we can imagine here. Now, because quantum computing today is not universal, we understand that the quantum power is really a limited commodity. And in the sense that if you don't really know what you're doing with a quantum machine, you will have a hard time really achieving the amazing results that I was showing you in my first or second slide. So at QuEra, we take a holistic approach to quantum computing. Here we build hardware. This is a picture of our 256 qubit quantum processor that is going to be available this year. But we also have an algorithms team that develops solutions to run on this hardware and to support customers in creating solutions that really extract the most of this hardware, okay, the most quantum advantage, if you want to call it, from this hardware. And we have also a software team that builds tools and builds cloud access to enable, at the end of the day, our customers to operate the algorithms that they develop with us without having to have all the full expertise that our algorithms team has on our platform. So we're really trying to squeeze all the quantum value that we can get out of these machines. Today, quantum computing is not general. We have to have a sort of a matchmaking process between problems and technology. And the hardware efficient applications for this particular technology falls into two main directions. One of them is network design problems. And this direction is really a pretty broad range. It involves automation, logistics, telecom, but also pharma, genetics, finance, and many more. And what we have on the other side is what I call problems that are born quantum, right? So problems that from the get-go, they have a strong quantum component to it. So new materials, sensing, chemicals, and so forth. Now, if you want to access our machines, and I should encourage you to be excited about this access, we have also a holistic approach to it. One of them is, if you understand the point that I was making, that you really want to take a strong expertise on how to operate these machines to develop to extract the most value out of them. We have a direct partnership program where you can join us. We can help you figure out what is the best business direction for you to follow in quantum and develop those applications, co-develop with you, educate your team if necessary, and deploy what can be a solution, can be some piece of IP, can be a paper or whatever is really your business is interested in. Conversely, or alternatively, if you feel independent and ready to go, we are really providing democratic access to our machines via Amazon Web Services this coming summer. So given that, we have a very strong network of different groups that are engaged with us, that understand our value proposition here, that it's better to work directly with us. And we are really expanding on this network of clients and partners. So I encourage you to reach out so that we can find the direction to work together. And my final words is that we have machines that are really, they have their utility as at the core of their design, really. We are creating machines that are really here coming to bring direct value to different business cases. We have a lineup of products for the summer, including an emulator, an efficient emulator based on Julia language that has been just open sourced last week, and cloud connected QPU. And what I consider a stronger value that we bring here is a top tier team that will support you in the development of your applications in start and follow your quantum journey. So yeah, please do reach out to us, and I'm happy to stay around and take more questions and have a nice conversation later. Thanks.
I'm Paul Lippman, President of Quantum Information Platforms at ColdQuanta. So a bit of background on the company. We're probably best known for designing, developing, and manufacturing products for trapping, cooling, and manipulating atoms, and also ions as well. The glass cell on the screen here is one of that product set, and we sell those to other quantum companies in the ecosystem, to researchers around the world. We also use those products to create a variety of quantum platforms, from quantum computing that I'll talk about today, our unique quantum dynamics platform called Albert. We have a number of initiatives in quantum sensors, from inertial sensing to RF sensing. We develop optical lattice clocks, some of the most precise instruments ever developed by humanity, and a number of initiatives in quantum communications. And the longer term vision for the company is to connect these quantum sensors with quantum computers and quantum signal processing platforms via quantum networks to solve some of the largest problems facing the world. Atoms are a particularly attractive approach for building gate-based quantum computers. We pack them together, as has been said, in these very tight two-dimensional arrays. In fact, the core of our QPU is the glass cell I'm holding up here, which could hold tens of thousands of qubits, and we're cooling them to microkelvin with lasers. So no cryogenics. They have very high connectivity across the array, will ultimately scale to over 100 to 1 and beyond in terms of connectivity, which will give us a variety of very compelling approaches for more efficient error correction codes. And then lastly, and perhaps most importantly, the core of the QPU is the glass cell I showed you before. The rest of the computer is optics, it's photonics, it's electronics, all of which can be miniaturized. And actually, we had experience miniaturizing at ColdQuanta. We've put quantum systems on the International Space Station, and our goal over the next 5 years is to take quantum to the edge and deploy these powerful quantum computers as rack-mountable devices. We've achieved a number of really compelling industry firsts in cold atom computing. We have a paper that was recently published in Nature, along with our academic partners and with Riverlane, demonstrating for the first time the execution of algorithms on a neutral atom platform. We have another paper that just went up on the archive, where we've demonstrated the largest ever trapped array of atoms, over 1,200 atoms trapped, and those are precursors then to becoming operationalized qubits. And we will shortly announce the world's first commercially available gate-based cold atom quantum computer called Hilbert. In terms of where we're going longer term, by 2025, our goal is to have 1,000 qubit device. And as I've shown, we've already demonstrated that very critical precursor step of trapping the atom array. And by the end of the decade, our goal is to be in the region of 1 million qubits. And as I said, those individual modules, those glass cells, can hold tens of thousands of qubits. So to get to the 1 million qubit range is a fairly modest number of QPU modules, as opposed to some other modalities that require enormous numbers of modules and all of the complexity around connectivity. In terms of our interests for the QED-C marketplace, we're always interested in engaging broadly in the quantum ecosystem, certainly with customers, whether it be for getting access to the Hilbert cloud system, for the underlying components, the physics packages, the ion traps, the glass cells. We're talking to a select number of customers and national programs about full stack quantum computers that we would deploy on premise. And then on the partnership side, we partner very broadly in the application and software space, and certainly always interested in working with partners to bring added value to our customers. So thank you very much.
Thank you for your time, everybody. I'm kind of sad we only have a few minutes per company. It's been great hearing what everybody's doing. Wish we could have like an hour session on everyone. I can't believe how much the field has actually advanced in like last year since the last time I did something like this. We're Xanadu, and like everybody else here, we're doing something different. It's great to have lots of different approaches. Our mission is to build a quantum computer that is useful and available to people everywhere. And it seems like a pretty straightforward mission, but both those useful and available pieces are actually incredibly challenging. We work in a slightly different approach. Ours is photonics, so using light. And that has some fundamental differences, advantages, and disadvantages. We've been around for a while, founded in 2016. Uniquely, maybe that we're another Canadian company located in Toronto. And today, I think it always changes day to day, but we're somewhere over 130 people, mostly focused on hardware, but also working on our applications and software stack, which is open source. And you can check out some other QED-C videos on Penny Lane. Photonics does offer some unique benefits, and probably the biggest one is one that was just mentioned by ColdQuanta, which is this idea of scalability. When we're talking about scaling here, it's not from tens to hundreds of qubits. We're really talking about scaling to millions of qubits. And it's because we need millions of qubits in order to be able to actually facilitate the truly transformative power of quantum, not the marginal quantum advantage that we're chasing today, but really, using Shor's algorithm to break encryption codes, that level of work. And getting to that number of qubits, we already are quite aware that all existing approaches are not able to put all those qubits onto a single chip. So you're going to need to be able to interconnect chips together. And this is really where photonics shines, mainly because the interconnect between chips has already been a somewhat solved problem for quite some time. In fact, the first quantum computers we stood up online with our X series GBS devices already were moving in quantum information between two chips in actually two different rooms. Another really big advantage of photonics is room temperature operation. And you can really imagine the future where you have edge deployed quantum computers. But what it means today is that we're just able to develop a lot faster. Our chips look very similar to the semiconductor chips that you have in your computer today. And in fact, we can use all the same infrastructure to test and validate our designs that has been developed for the semiconductor industry. Similar to that, that same benefit of kind of being really compatible with the processes means that we're also highly manufacturable. When you think of that million qubit quantum computer, it's going to be many components, many chips. You actually need to be able to manufacture these at scale. You could have the best qubit in the world, but of course, if you can't make it, it's not really going to be useful to anyone. And we're really lucky here in photonics that we're standing on the shoulders of giants, the billions of dollars that has been invested in telecom and datacom. And this really allows us to work with the largest foundries today. If you take a look at some of our announcements, you'll see that we already have partnerships with folks that can deliver the volumes that you will need not only to deploy a single large scale system, but actually many. And maybe the last one is a little unique. Our friends from IBM touched on it, but clock rates will eventually matter in quantum computing. Today, they don't because we're tackling bigger challenges. But once you get to fault-tolerant universal systems, there will be a clock race. And the really great thing about the photonics approach is that the limit to how fast you can go isn't actually the quantum part, it's the classical electronics that are controlling our quantum systems. Photonics is naturally broadbanded. We use it for the highest speed applications today, and that transfers over to working with quantum information as well. So our past was really focused on building the core components. You can think of it as maybe the transistors of our architecture and getting them to quality and manufacturability that we can use for a broader architecture. Now in the phase that we're actually building the first module that can actually demonstrate those fault-tolerant pieces. And once we have that, I would say the engineering work has been de-risked and really turns into a manufacturing problem to deploy that large scale data center. I'll briefly go over because it's a little bit different, but it'll be really kind of a high level fly through of how this architecture works. If you're interested, you can also check out our YouTube channel where there's a little explainer video. But basically, photonics is unique in that you don't hold your qubits on the chip, mainly because they're made of light and light is continuously moving. So you actually are continuously creating and destroying your qubits. And the quantum information persists because you're actually able to teleport it from one qubit to another. So one of the most important and probably one of the most difficult parts is actually making your qubits in the photonic approach. And we use this state generation factory. And what it does is it gets excited with classical light. And what it outputs is a series of quantum states. Squeeze states is what our old quantum computers leveraged for GBS applications. But there's more complex states called GKP states that are, I would say, very robust qubits. Once they are generated, unfortunately, these really robust qubits are generated with probabilities that are a little lower than we would like. So you actually need to increase their probability by taking many generating devices and multiplexing them, combining them together in order to increase the probability. This then allows you to move into the stitcher. And here you can think of as the part of the quantum processor where we actually generate all the entanglement. So all the qubits that we're generating in the layer above, and you can imagine each one of these sources putting out a qubit every clock cycle, we're now going to stitch and we're going to entangle them not only spatially between each of the qubit sources, but also through time. So a qubit that was generated on the previous clock cycle is connected to the one that follows it. And this gives us a very nice, large, three-dimensional, fully connected lattice of qubits. And then simply to operate on this with any sort of user program, all we need to do is measure these qubits in very specific ways. This can not only implement the user program that we're interested in running, but also all the error correction, all the diagnosing of potential errors to actually support fault tolerance. And the great part about this is that the detectors that we need here are actually the same type of detectors that modern LiDAR systems use. Again, fully manufacturable, accessible technology. This approach in general is called measurement-based quantum computing or one-way quantum computing. It has really exciting possibilities in being able to push better error correcting schemes as well due to the much deeper connectivity. But one of the maybe very important things to note is that from a fundamental level, it is fully equivalent to the qubit on chip approaches once you're looking at a fault tolerant universal system. I'll pause there, but if you're interested in learning more, whether it be to get access to our current devices, whether it be to talk about our software stack or the applications work that we're doing, I would be thrilled if you reach out to my colleague Sean at Xanadu.ai, and really looking forward to the broader discussion.
We just finished the lineup, and now we're going to go into the panel discussion. So I want to start with Jerry. So IBM Quantum, are you a full stack quantum computing provider? And one question as part of that is, can a third-party software for quantum provider or providers work on your platform?
Yes and yes. So we have our hardware, right, as the base layer, right, and then we have our open source software stack Qiskit with the various different APIs for different developers, as I showed in the probably flash. It didn't get enough time on the screen, but to
Sure.
different levels of APIs for access, right, for different types of developers and different types of software companies to bring in their value, right? So those that might want to work at the kernel level to develop better pulsing or better circuit noise mitigation type of developers, and those types of companies would work there, and also on application basis from the top too.
Yeah, great, thank you. Murray, you care to comment on this?
Yeah, absolutely. I mean, the easy answer is absolutely. D-Wave's a full stack quantum computing provider. We're providing quantum computing systems, software, and services to help people with mapping their applications and getting demonstrations of business value. Our technology stack leads up to our Ocean open source software, which is Python based, and you can install it with PyPy, but it has a lot of C++ components for speed under the hood. And there are a number of ways that third parties can contribute. So we've actually had companies like Recruit in Japan and teams from Los Alamos National Laboratories that have actually contributed components to our Ocean library that have been incorporated. We've got folks like AWS Bracket who have actually developed toolkits to help people with programming the quantum computing systems, and they have created extensions to our cloud client for people to be able to submit jobs to Amazon Bracket and our quantum computers there. And also in the case of those who are really familiar with the IBM Qiskit platform, we have extensions of the IBM Qiskit platform so they can formulate problems there and submit them to D-Wave quantum computers that way. So really it's quite robust, and there's lots of opportunities for people to be able to access the programming. I should also point out for researchers who have expertise that really applies to certain areas of the technology stack, because it's open source, you can actually go in and make improvements to some of the components of the technology stack. And what's great about that is that everyone who's building applications on top of that gets the compounding benefit from the contributions from all those researchers at every point in the stack.
Yeah, great, thank you. Brian.
Yeah, I would say we are a full stack provider. If you have circuits you want to run today, you can go online and submit them through the cloud and get results back. We also have now, with this merger with Cambridge Quantum, we now have a lot of opportunities for work, co-work on algorithms. And we've inherited a lot of the ability to do sort of quantum circuit optimizations with Ticket and other platforms over there.
Mm-hmm. Great. Pedro.
Well, I guess this was explicit in my slide. So yes, we are definitely a full stack quantum computing provider. And the answer to the second question is also yes. In principle, our machine is going to be firstly available on the cloud on AWS in the coming few months. And yeah, you can definitely create a third-party software and operate them directly on top of the API from via Amazon.
Fantastic,
Paul.
Yeah, I think we obviously need to be careful about how we define full stack, but certainly we have an algorithms and applications team that works with customers to enable them to solve their problems on the Hilbert platform. And if you go back to the previous slide, so I could see the second question, I think the question was, yes, can third-party software? Absolutely. So when we launch Hilbert, as I say, very shortly, that will initially be using Qiskit. It will actually operate through our own cloud platform that we've developed, but certainly have plans. We've announced integration with StrangeWorks, and we will announce other integrations in the very short near-term future. And in terms of third parties, as I think I mentioned, we work with Riverlane extensively, have integrated their software and others that we'll announce in the coming weeks and months.
Great. And then Raf.
I mean, you see the trend, of course. We're a full stack quantum computing company. I'd say uniquely, we have one of the major open source software frameworks for quantum computing in Penny Lane. Encourage you to check that out. Maybe one slight differentiator for us is the way we approach our customer engagements is a little bit different. We really only do things that are very technically aligned with our technical roadmap. We're not looking to be a consulting company. We're looking to tackle the kind of most challenging problems out there. We also want to give a shout out to, we do work with quite a few companies here from the hardware side, mainly to support Penny Lane and make sure Penny Lane connects there. And everybody, I'd say, has been very open about access to their hardware, making sure that there's interoperability between hardware and various software platforms.
Great. Okay, so let me start this time with Murray. So how does a customer today access your cloud platform, and what does that look like?
Yeah, absolutely. So right now we have our Leap cloud service that's available. So if you just go to your favorite search engine and search D-Wave Leap, you'll find a variety of links that will take you there with information about it. When you click on that, you can sign up and get free immediate access to our quantum computers. And by immediate, I mean that you can submit problems and demos right there in Leap through the interface and through our integrated developer environment and get answers back immediately in seconds. So you don't have to schedule the time later in the week or anything like that. And if you are willing to open source your code, if you're working on a project that you want to contribute to the open source community, you can link that project and we'll continue to provide you with that access each month, renewing your access each month. And if you're looking for access under commercial terms, you can actually absolutely contact us and we can work that out with you so that you can get continuing access to the quantum computers that way. It's also available in Amazon Bracket, so there are folks who can access it through that service for Amazon users. You can find support online and user portal and community as well for when you're looking at that access and getting started with your programming. And I should also mention that we have training courses available for those who want to learn about problem formulation techniques and problems that are suitable for quantum computers.
Great, great. Pedro, you mentioned that your system's going to be on Amazon AWS Bracket as well, right? And that's later this year?
Yeah, exactly. So you'll be able to access it on the cloud that way. And the way it's going to look like is going to be via the AWS API that is in development. Otherwise, you can access it directly through us, where, by working jointly, we will operate directly in our machine and encode the problems.
Great. So Jerry, how does one access the IBM Quantum platform these days in the cloud?
Yeah, so through our IBM.com quantum computing, you can access, you can right away just access a few backends that are for free. Then we have other systems which are accessible through our quantum network. So that's through certain hub organizations which one can get affiliated with in order to get access that way, or become a hub member themselves. And then most recently, just 2 weeks ago, we announced a new way, which is a pay-as-you-go offering, where effectively within IBM Cloud account, you can access our Falcon processors now. So 27 qubits on a circuit by circuit basis.
Great. Raf, Paul, care to comment on this?
Sure, I'll jump in. So as I say, we'll be launching Hilbert very shortly. You'll be able to access that through ColdQuanta.com. We have announced forthcoming integration with Strangeworks and others to follow. We have another quantum system, which is our quantum dynamic system I mentioned before, called Albert, which is not a quantum computer, but it's a cloud system where you can create Bose-Einstein condensate, experiment with Bose-Einstein condensate, and ultimately longer term use that for designing quantum sensors and quantum instrumentation. And I'll drop the URL in the chat because that's available for public free access right now.
Great. Raf, Brian?
Yeah, from our side, I think we've had our first quantum computer online for now 3 years. We're closing in on that. I'd say if you're interested in access, feel free to reach out. Happy to get people connected, especially for researchers looking to do something novel. Always looking for great people looking for applications.
Does it cost anything?
I want to say it depends who you are and what you're doing.
Yeah.
So I mean, very honestly, it comes down to that. A lot of times when we engage with customers, they tend to be high touch engagements to drive success.
Sure.
If there, of course, it costs things. If you're a high quality researcher that already has a great proposal in mind, we would never want money to get in the way of great work. So there's definitely ways to work together.
Great. Brian?
Yep. So we have a web API. You can access our system directly with that. And then we're also available on Azure Quantum.
Yeah. Great. Okay. So I'm going to go with Jerry first on this one. How does IBM define quantum advantage, and and where do your customers see this happening now or soon?
Yeah, I was just answering one of the questions in the Q&A. That was kind of along that lines too. So I think the whole point here is that quantum advantage is the way that I define it is that you can do a problem more efficiently, faster or cheaper than you would do with any sort of classical means. And the key thing there is really we know that there are quantum circuits that can have a quantum advantage, right? There are complex enough quantum circuits that if you have a large enough register of qubits, that you will see and experience a quantum advantage. The key thing though is how do you handle the noise, right? And especially there's strategies towards that. In the long term, right? People talk around the concept of fault tolerance, and certainly the ideas of error correction comes into play. But also in the near term, we've continued to develop a lot of noise mitigation methods, including probabilistic error cancellation, as well as zero noise extrapolation, which allow us to handle real world noise on the systems that we have today. And that combined with continuing to push the quality and the scale and speed of our devices, we expect to see quantum advantage. I think as we are rolling out these larger systems that are capable of running some of these circuits that you're just gonna struggle to simulate.
Yeah, great. Brian, how does Quantinuum look at this? How do you define it?
I think our definition is very similar to what Jerry just shared. Are you solving a useful problem that cannot be solved any other way, or solving a problem that you can do quicker? I think we're looking at seeing some quantum advantage in this era over the next few years as our systems get larger. I think exactly how far we can push that without quantum error correction is definitely an open question at this point. But I think the next few years of development on the algorithm side is going to be key for this as well. As we build bigger and bigger systems, are we coming up with more and more clever algorithms to take advantage of the unique features of our systems now that sort of close that gap between application and hardware?
Yeah, great. Murray.
Yeah, I think my answer is probably going to diverge from Brian and Jerry. So I would say that generally speaking, what we sort of see is that the interest in quantum advantage is largely from academics and researchers. And most people who are looking at applications and practical business value are looking at sort of like commercial advantage. So they're really looking for a situation where they can build a solution or an application that can incorporate quantum computing, and they can actually do better than the way they're operating right now. They're looking for improvements in efficiency. They're reacting to these supply chain disruptions, so they want to get more robust. They're looking for places where that's going to be. We've already been able to do demonstrations in quantum material simulation where we're 3 million times faster using our quantum annealing systems than the best classical alternative. That's plenty of advantage right there. But probably what's most compelling for businesses is like that entire advantage materialized in 2 product generations. So we went from not being able to simulate the properties of those quantum materials to being 3 million times faster at it 2 product generations later. And so what that means for businesses is like, if that can happen, if you can get that kind of disruption in your business, you want to start exploring and incorporating these hybrid technologies. You can build applications that are going to leverage that growth and capability over time. Now, that particular experiment, there are lots of cases where you can submit problems for our quantum computers and you can outperform classical alternatives to those. But I would say that like long after you have demonstrated a business advantage with quantum computing and quantum hybrid technology, there's a huge bar, like technical bar, that needs to be surpassed to prove that quantum mechanics was the only way that you could have gotten that advantage. And quantum mechanics played a pivotal role in the solution finding in that particular node. We've passed that bar with some of these simulations and papers that we've written on quantum material simulation, but it's definitely not the places that we see businesses starting. So their care about, it's much more about commercial advantage. And I think that quantum advantage will emerge naturally over time as we continue in this field.
Great. Thank you. Pedro, you had some comments on this, I know.
Absolutely, yeah. So I guess I would do a little combination of the answer of everybody up to now. Indeed, the definition of a physicist or a mathematician, and being a physicist myself, I know that that definition can be stringent, but from a business perspective, I think that quantum advantage can go much farther. Not only speed, but an extra ingredient that can be included here is accuracy. There are certain solutions that say you're doing some genomic mapping that the current heuristics that people use frequently don't have any guarantee for the quality of the solution, and a quantum application on there can actually have a better generate a better valuable, a more valuable result to the problem. So I think that quantum advantage is really about enabling business cases that your competition simply doesn't have. Sometimes that involves doing things faster, but speed is not necessarily the only variable here. Where do I see customers seeing this happening? from an academic perspective, I believe that we have several indications today, not only from QuEra and QuEra's partners, but from several other groups around. So this will become, the way I see this, is a reality today, and this is going to become more and more widespread in a matter of 1 to 2 years. Really, it's not. This conversation is going to be less. More flexible in 1 to 2 years, let's say.
Okay, thank you. Raf, Paul, you want to add anything on this, or are you good?
I'll just jump in.
Yeah,
I'll just jump in with one final point on it from my perspective, and I agree with what's been said so far. I think one of the really interesting areas where we may well see some near-term true advantage is at the intersection of quantum sensing and quantum computing. There's been some recent academic research that's demonstrated advantage there, exponential advantage. It's certainly something we're looking at as we kind of live at the intersection of those worlds. So I think we kind of need to take maybe a slightly more unconventional view, and to the points made of business advantage versus technical quantum advantage. And certainly at that intersection of sensing and computing, there's lots of room to really drive real advantage for users.
Yeah, no doubt with networking and sensing and timing that there's some big plays there, but we were going to primarily focus on computing today, but you're absolutely right. Raf?
Yeah, maybe just one thing. I still think that there's a big cliff that we're looking at with fault tolerance. A lot of things we're talking about today were, I'm not going to say they're marginal, but they're incremental gains over classical, whether in terms of breadth and the number of applications, or in terms of the actual amount of speed up or accuracy that you gain. There's been a lot of great theoretical work done, meaning that there is a series of applications sitting. We know how far out now. There's been great resource estimation, but we need to build the hardware. So there's all the great incremental work that's happening, but with fault tolerance does come a truly transformative moment. I mean, I think it'd be naive to say that it won't be as impactful as some other transformations like digital computing or, connectivity of the internet. But that really gets unlocked with that fault tolerant piece. That's where I see the real term.
We're going to talk about that too. So, okay. So I'm going to start with Jerry on this. So, what are the economical potential applications of your technology to NISQ? And not everybody may know what NISQ is, so I define it at the bottom as noisy intermediate scale quantum, right? Base computation or simulation annealing. Any comment there?
Yeah, I mean, I actually don't like to use the word NISQ, right? I mean, it's
it's used all the time. That's why I put it there. But
yeah, I know,
sure,
I know. It's become part of the vernacular. My main concern with it is that there are different models of quantum computation, right? So annealing is different, obviously, from the circuit model, but NISQ is not different, right, from the types of systems also that we're looking to build towards fault tolerance and quantum error correction. It really just refers to this kind of period of time right now that all of a sudden we have systems that are more readily accessible, right? But I actually think that there's not going to be some kind of like phase transition that, all of a sudden we're going to have fault tolerant quantum computers, right? What we should be seeing is that we are going to continue on this roadmap of technological development where we will improve the running of and the accuracy of running quantum circuits. And so the economic potential comes from finding those quantum circuits that drive potential advantage, right, in particular areas. And I think we can group those areas pretty concretely, right? There's certainly the simulating nature, right? And there's known circuits that will drive advantage for those types of simulation of nature, which will impact, obviously, right? We talked about drug design, all these things, all these really fantastical phenomenal things. Then there's also data with structure, right? And handling basically learning and machine learning of structured data, right? Where we know that also there are robust potential speedups using quantum computers and quantum circuits. Interestingly, like Shor's algorithm falls in that type of category too, of looking at some type of, it's basically the modulo function, right, which is the structural element of the data set that you're looking for when you're solving a factoring problem. And then the third area would be like what we generally kind of, call optimization, right, which is like a quadratic speed up, not quite the robust exponential speed up, but still potential gains with things that might use, Grover-based algorithms. But really, the whole point is recognizing these circuits of value, finding ways to make their estimations, right, or running of them on hardware that we're building to be more robust and more accurate.
Yeah, great. So Murray, you guys have been at this a long time. What are you seeing?
Well, I think this is exactly the right question for us all to be focused on as a broad industry, not the technologists, but like the technologists plus all the users and all the industry businesses. If you look at the amount of money that's put into, let's say, GPU development, I think NVIDIA has spent something like $2 billion on the latest GPU processor, and that's the best GPU processor that's ever existed. But I've been playing video games using GPU processors from NVIDIA for 20 years. So you might ask the question like, well, why didn't they just build this processor 20 years ago? And that's because it didn't cost them $2 billion. It cost them every generation and all the money they've spent on every successive processor they've built so far, plus that $2 billion to make that. And the reason that they have the ability to build this processor is because they were able to produce value for their users at every iteration along the way. And that's what needs to be happening with quantum computing. That's exactly why we're so focused on practical quantum computing that brings people real business value in their applications right now. There has been a lot of work by the Boston Consulting Group looking at the total addressable market for quantum computing, and there's going to be applications in the area of optimization. There's going to be applications in the area of like quantum simulation and in differential equations. What's now known experimentally, we've seen papers written with experimental investigations and mathematical investigations, is that for the purposes of applications that involve optimization, some of the examples I talked about with sustainability for waste collection and also for supply chain logistics with the optimization of the operations of the Port of Los Angeles, is that quantum annealing is going to be the only quantum computing platform that's going to be able to effectively address those. And that's primarily because of all the programming models that involve gate have such a huge overhead in the parameter tuning steps. It actually negates the advantage you get from using the technology there. However, there are really important applications if you think about discovering new drugs, where you're going to need to be able to use gate model-based quantum computers so that you can do the fermionic molecular modeling that you need for that drug discovery. And then later in that process, you're going to be optimizing drug trials. And so really, you're going to be using multiple technological modalities as you're bringing that application and that value to market. What we should be focused on here is not technology-led inspiration for application, but application-led inspiration for the technologies, which is that users should be coming to our cloud services, looking for those open source examples that show them how applications are approached. And then we should be bringing the technologies that bring the most potential to that, whether that's annealing-based, gate model-based quantum computers, or even classical computing technologies, and really combining these all together so that all of their strengths are brought to bear for the greatest advantage for our customers.
Great. So Paul, I realize your system is not on the cloud yet, but how is ColdQuanta looking at this?
Yeah, I mean, I think I'll echo what's already been said. I think, frankly, it's kind of day one still in the quantum computing industry. I mean, notwithstanding the fact that IBM's had systems on the cloud for, I think it was the 6-year anniversary somebody mentioned, we're still so early. I think the applications and the business benefit from these systems over the next, call it 2 to 3 years, will be in areas that we may well not yet even realize. And it will be that experimentation from early customers, that exploration of use cases, and the exploration of differential use cases between the different modalities and different configurations that will point the way to useful production business opportunities. I'll say also, I think we need, as an industry, to evolve our view of benchmarking and kind of moving away from the kind of scalar value or the kind of single measure of computational capability to benchmarks that really model the actual reality and the actual business problems that customers are trying to solve. Because certainly today, when we talk about kind of the usual suspects of these early adopters, these are folks that have quantum experts, that are building teams of quantum physicists or quantum programmers. For us to kind of cross that chasm to the larger opportunity here, businesses are going to ask the question, well, how does this solve my problem? And how do I choose the hardware platform that will best address the business problem, and whether that be from the standpoint of speed or accuracy or modeling fidelity will be very much use case dependent. So we're going to need to see these benchmarks evolve to be able to address those questions.
Yeah, and I'm going to jump to the next question. I know we had a few that didn't answer here, but unless one of you feels really strongly about it, I want to get to a more the next point. Okay, so we'll do that. So what is your pathway to fault tolerant quantum computing? I'm going to start with Brian on that one.
Yeah, so we've been focused on fidelity first and foremost. I think that's important to get these fidelity of your physical operations as low as possible, while at the same time developing a system that can scale up in size. So you can build up a system large enough to do large scale quantum error correction. I think there's a lot of problems to solve, and all the different technologies. I happen to like the problems we have to solve with trapped ions, but yeah, if the fidelities are low and you build these demonstration systems, you can figure out what the best methods for quantum error correction that match your hardware are, and then I think we'll pull down some of the requirements that have been tossed out previously as we get sort of smarter error correction models to match the capabilities of the hardware.
Great. And Paul, I'm going to come back to you on this. I know ColdQuanta has a lot of thinking on this. Why don't you share what you think there?
Well, I'll share a little bit, because there's a lot of that that's happening kind of behind the scenes. I think there's multiple paths to fault tolerance, and certainly, as I mentioned in my comments earlier, with high connectivity comes the option for more efficient error correction codes. And then from a hardware perspective, we're looking at actually have testbed systems in the lab right now that are looking at a variety of options and atomic species for fault tolerance. So it's kind of one of the, I think, and no doubt my colleague from QuEra will agree, it's one of the attractive aspects of the atomic approach to quantum computing, is that we have a variety of options here for developing logical qubits and potentially at ratios of logical to physical qubits that are significantly more attractive than some of the others that you may have seen in the academic research to date.
Yeah, great. So Pedro, thank you, Paul. So Pedro, you're also doing Neutral Atom, your company.
Yeah.
Anything you want to add on what Paul said?
Yeah, absolutely. There's quite a few things that I would like to add here, because indeed I agree with my colleague here that the flexibility of the Neutral Atom platform is one of key differentiators that enables us to think about fault tolerance and scaling without having to redesign the chips and redesign everything every time, right? So it's a modular architecture that only gets better, right? And I think that a point that is frequently overlooked is really the issue of reducing the amount of gates necessary for calculations, because even if you crank the nines in fidelity, reducing the number of gates is a crucial aspect. So to basically manage the errors, and the flexibility of the neutral atoms, and in particular of this idea of shuttling atoms around, which we introduced a couple of weeks ago. So we were the first ones to propose a fault tolerant and demonstrate the basics of fault tolerance applications in quantum computing with our colleagues from Harvard. That is crucial. So a point that is fundamental here is, at the end of the day, that being able to separate memory from processing is crucial. Okay, that's what's going to allow you to encode process information with as few gates as possible, and with gates of course of as high quality as possible, and separate that from a memory side that really just survives the quantum coherence as we go through the quantum algorithm. But I think that's the pathway that we see for neutral atoms, and I think that it's uniquely promising.
Okay, great. Raf.
Yeah, I mean, from our perspective, this has been a focus from day one.
Yeah.
I'm not sure if I'm frozen here. I appear frozen to myself. I apologize if I am. I'd say for us, it's not only about the architecture, which we published a year and a half ago, and again last year, an update to it. It's not only about the hardware and the kind of base fidelities, which we've been working on hard and can be assessed with our early devices that we stood up online. But it's also about how do you actually build this system? Definitely through the explorations of all the different architectures we could take with the photonic platform, which there are many. There's a lot of ones that you can take that are attractive, but in fact, you would never be able to build at scale. So our focus is, doing everything now in lockstep, building that first fault-tolerant module to not only make sure that as we scale up, we're able to tackle the issues around noise, not only that we can build it, but also that the architecture team has really good feedback to understand what advancements they need to make in order to push the hardware requirements down. We're really excited about the progress, and like the folks in the neutral atom world, one of the big advantages of photonics is that there's a whole unexplored space of error correcting algorithms that need to be tackled. So if there's researchers out there looking to create a great new company, I would say definitely looking at error correction is probably going to be the next era of quantum software that'll be really impactful.
Yep. Thank you. And then Murray.
Yeah, so we're taking a 5-phased approach to producing a fault-tolerant quantum computer, and we're really trying to accelerate directly to that end goal as quickly as possible, just precisely because if there needs to be a NISQ phase, we want that to be as short as possible, and it's not super duper clear yet where we can get the sort of economic value out of that for our customers. So what we're primarily focusing on to begin with is that we have like a very advanced superconducting multi-layer stack. So we want to validate our gate model of quantum qubits in that multi-layer stack. The second phase is really about then validating the on-chip control of those systems and then validate the error correction. So we want to get through those 3 phases as quickly as possible, because that will allow us to then demonstrate logical qubit manipulation. So a logical qubit is one which is a combination of multiple devices, which allows you to create an error-corrected qubit. And it's one of my colleagues have been referring to. That's part of the reason why so many of our implementations are looking at scaling to really large numbers of devices. Once we can get through that demonstration of the logical qubit manipulation, then we can start designing scalable task-specific components for a processor. And DWAVE has a lot of experience with building processors that are going to be working in application workflows at full scale. So that approach there, the qubit validation multi-layer stack, the on-chip control, the error correction, the logical qubit manipulation, and then the task-specific components is our main strategy and plan on our Clarity roadmap towards delivering these error-corrected gate model.
Great. Thank you, Murray. Jerry.
Yeah. So I mean, I think my philosophy is a little bit different, right? Which is that the path towards fault tolerance, path towards error correction, a lot of that will be kind of guided by what we build, right? Like just from our own story, we built a particular lattice, this hexagonal lattice. Don't need to go into the details there, but then we worked out a different kind of error correction code that kind of fits to it. Really the whole point is that we know that there are going to be noisy issues with the systems that we build. But we also know that there are going to be primitive elements that we need to get working in a noise-free way to drive towards to unlock some of the full power of quantum computing, if you will, right? And so, like, I mean, just as another example, we have recently this work on probabilistic error cancellation, which is a path to actually giving fully noise-free observables on large circuits, at the cost of running, in this case, an exponentially larger number of circuits. But already we're talking about a trade-off of circuit time or runtime versus reduction of noise. And so we're going to find these types of interplays of trading off things for another. And that's going to guide also what are going to be the new fault-tolerant error correction codes and things like that will guide us in the future. And for that matter, like having primitives such as feed forward and phase estimation, right? Those and dynamic circuits are all going to be part of this picture for how we're gonna as we drive and make improvements in a roadmap and new hardware, it's going to then guide kind of how we handle noise and how we're going to build these we'll call them, more error tolerant quantum computers.
Yeah, great. So we're out of time here. So I'm going to just comment briefly. This was a fantastic webinar. Thank you, everybody. We're going to be running another batch of quantum computing system companies. At least we plan to on June 28th. That's coming up next. And with that, thank you.